So I would request all the participants to hold on for a few more minutes. Our speaker is yet to join, so we will wait for him also, and we'll start in a few minutes. So please hold on.
Am I audible, Dr. Vishesh?
Yes, you are audible.
Thank you.
So, a very good evening to everyone joining us from across the country. I am Dr. Shatarupa Bishash, Assistant Professor in the Department of Physics, Adamas University, and your host for this exciting evening. On behalf of Adamas University, I warmly welcome you all to the Day 1 of Physics Pulse 2025, a special outreach event dedicated to igniting young minds with the wonders of space science and physics. This event is specially curated for science students of classes 11 and 12 and freshers to physics, and we are delighted to have you all here today. So let us now begin the evening with a welcome address by our Associate Dean of School of Basic and Applied Sciences and Head of the Department of Physics, Dr. Momita De. Over to you, ma'am.
Thank you, Shatarupa. Am I audible?
Yes, ma'am.
Oh, just a minute. Good evening, everyone. It gives me immense pleasure to welcome all of you to Physics Pulse 2025. It's a two-day long celebration of exploration and the timeless wonders of physics, and organized by the Department of Physics, Adamas University. Uh, Now, a special welcome to all our enthusiastic participants, from school students to college freshers, science educators, and mentors from all across the country. We are truly delighted to have you here with us. And let us start this journey through space, science, and beyond. Now, today's online session, I must tell, this is a very rare opportunity. You will be hearing directly from the renowned scientists from NASA and ISRO, as well as leading expert in planetary and space science. This is your chance to meet the real stars of space science and understand how physics powers our understanding of universe. Now, as the head of the Department of Physics and at the Associate Dean of School of Basic and Applied Science, it's kind of customary. So let me take a moment to introduce our department. We are a vibrant research-driven unit offering undergraduate, postgraduate, and doctoral programs. And one special mention to the program post-semester diploma in medical physics, for which we received approval from Government of India, AERB, Atomic Energy Regulatory Board, last year. Now, our curriculum is aligned with NEP framework with hands-on labs, research projects, interdisciplinary electives, strong industry and institutional linkages. And our students have consistently secured position in IITs and ISRs. So as you all can see in different social media platforms. So physics, now today, I don't think it's about Adamas or our Department of Physics, it's about physics, this entire event, the Physics Pulse. So physics, as we believe, is not just a subject, it's a gateway to the new frontiers, whether it's exploring the cosmos or building next-gen quantum devices or simulating black holes. The future will be shaped by physics and the people and by the people who dare to ask questions. So I urge all of you today and tomorrow to ask questions, stay curious, interact freely, and most importantly, enjoy the session. Thank you once again and welcome to Physics Pulse 2025. Thank you.
Thank you, Dr. Dev, for your inspiring words. We are now honored to have with us Professor Dr. Radha Goswami, our respected Pro Vice Chancellor and Dean of School of Engineering and Technology, so to address the participants. Sir, if you are here, the virtual stage is yours. I think Sir is here.
I saw him a few minutes back.
Yes, yes, I saw him joining also.
Just a minute. Let
Is it that he is not able to unmute himself? Coordinators, can you please check?
No, he is not here at this moment. Maybe
Okay.
due to network issues.
Yeah, yeah. Okay, so maybe he will join us a few minutes later. So, do we have our speaker with us?
Yes.
Yes, please make him co-host.
Am I audible?
Yes, sir, you are audible. You are
Yes.
co-host now.
Okay, thank you.
Okay, so participants, now begins the most awaited segment of the evening, our distinguished lecture series featuring eminent space scientists and academicians from ISRO, the University of Texas, San Antonio, and NASA. So please note that we will have a question answer session at the end of all the three lectures. So participants are requested to keep their questions ready, and you can type them in the chat box also during the talks. So these will be taken up after the final lecture. Now let's begin with our first speaker. So it is my absolute honor to introduce our first speaker, Dr. Satadru Bhattacharya, a senior scientist and head of the Planetary Sciences Division at ISRO, the Indian Space Research Organization. So, Mr. Satadru Bhattacharya received MTech in Applied Geology from Indian Institute of Technology, Kharagpur in 2004. He is presently heading the Planetary Sciences Division at Space Applications Center, Indian Space Research Organization, Ahmedabad. His research interests include reflectance spectroscopy of rocks and minerals, lunar geology, planetary analog studies, and hyperspectral remote sensing for mineral mapping and exploration. His significant contributions include detection of magmatic water on the moon based on Chandrayaan-1, moon mineralogy mapper observations, and study of a suite of hydrous sulfates from the Deccan volcanic provinces of Kutch, Gujarat, and Puga hot springs deposits of Ladakh as mineralogical and astrobiological analogues to Mars. Dr. Bhattacharya, we are truly excited to hear from you. The virtual stage is yours.
Thank you, madam, and good evening to all. And of course, it is a very special day and auspicious day that we are celebrating Guru Purnima.
Dr.
So-
Bhattacharya, may I interrupt?
Yeah,
One.
sure.
So, can you please make it on the in the landscape mode, because it is appearing very small here in the portrait mode. Your slide, actually.
Yes, this is perfect.
Yes.
Now it has
Yeah.
been shrunken again.
Is it okay? Right now?
Yeah, this
Now,
is okay.
now it's okay. Yeah.
Okay.
Can you please skip through the
So,
slide once again so
well,
that we can check? I mean, the other slide as well appearing as it is.
yeah, tell me.
Can you please? Yeah. Okay. Now it's okay. Yeah, coming. Okay. Thank you very much. And sorry for interrupting.
No problem. So, good evening to all. And at the very outset, let me thank Adamas University for giving me this opportunity to interact with the students, especially of the 11th and 12th standard, if I'm not wrong. This is our slide. We are a small group of people here at Space Application Center, ISRO Ahmedabad. This is one of the major ISRO centers in Ahmedabad, and we'll be shortly seeing that what actually we do here at Space Application Center. So, as you can see in the title slide itself, this is a small group which is called a Planetary Science Division. We are into the business of planetary sciences, and we use the remotely sensed data from various missions over Moon, Mars, Venus, and so on and so forth. And we try to analyze those data sets and to come up with some kind of meaningful science from all those missions and data. Our emphasis is, of course, the sensors or the payloads that we fly in our ISRO's mission. And apart from that, as an ancillary data sets, we also use the data that are available from various space agencies missions. And so I'll just quickly move on to the next slide. So, as the name suggests, the Space Application Center is primarily responsible for building the sensors or the payloads for any ISRO missions. to the remote sensing Earth observation payloads, as also the communication transponders. And here, this particular slide is showcasing the payloads or the sensors that were being flown in Chandrayaan-1. And we had quite a bit of payloads like terrain mapping camera, then hyperspectral imager, then lunar laser ranging instrument, and high energy X-ray spectrometer. These are all from Indian side. So out of this terrain mapping camera, high C or hyperspectral imager, and a little bit of part of this moon impact probe. These are all jointly and exclusively built by Space Application Center. And then we also have quite a good amount of instruments on board this Mars orbiter mission. And to name a few is that Mars color camera, then thermal infrared imaging spectrometer, and the methane sensor for Mars. And then comes the Chandrayaan-2, which is right now orbiting the moon. And it is also having 4 crucial instruments from Space Application Center. And the first one is the orbital high resolution camera. This is obtaining the image of moon at the highest available resolution, that is 0.3 meter from 100 kilometer altitude orbit. And it is giving us almost a ground truth kind of data sets over the lunar surface. This is originally built to help in assisting the soft landing of Chandrayaan-3. And now many signs are also being brought from this instrument. Then we have this imaging infrared spectrometer. So we mostly focus on the visible near infrared part of the spectroscopy, and it's also called reflector spectroscopy. So this particular spectrometer is again built at SAC, and it is having a spectral range from 0.8 micrometer to 5 micrometer. Then we have this dual frequency synthetic aperture radar. And this is a very unique instrument, I would say. And this is for the first time Space Application Center has developed a dual frequency synthetic aperture radar in both S-band and L-band. And that too, the L-band radar is basically a fully polarimetric instrument. And that is for the first time ever flown on Moon. So it is gathering fantastic data sets, and those data sets are being analyzed and published time to time by various researchers. Then we have a terrain mapping camera 2, which is almost the same version as that which was flown in Chandrayaan-1. So it is basically a stereo camera. It has got 4 aft and nadir, 3 viewing geometries. And using the principle of stereoscopy, we can generate very high resolution DEMs of the order of 5 to 10 meters of the whole of Moon. So rest, many of the instruments are also from the other ISRO centers, like URSC has provided the soft X-ray spectrometer called CLASS. Then we have the X-ray solar monitor provided by Physical Research Laboratory, Ahmedabad. And then we have CHES-2 for studying the neutral atmospheric compositions of Moon. It is provided by SPL Trivandrum DSSC, Vikram Sarabhai Space Center. So these are the things that we, so in case of SAC, I would say that we have dedicated areas or entities that are into the business of building the payloads or the sensors for various ISRO missions, be it Earth observation or communication, and also the planetary explorations. And apart from that, these are the pictures of those instruments which are flown in various ISRO missions. And then we have a dedicated area or entity that is taking care of the signal and image processing and data processing. And then finally, we have a team of application scientists who are analyzing these various data sets. So there are expertise from agriculture and ecology, environmental sciences group. Then we have geosciences group, planetary sciences group, then atmospheric and oceanic sciences. So there are almost an entire gamut of applications you would see in Space Application Center, as the name suggests itself. So overall, if you look into the planetary sciences activities, our main goal is to understand the original evolution of the solar system objects. And right now we are mostly concentrating on the inner solar system objects, specifically on Moon, Mars, and Venus. So ISRO is gearing up for its maiden Venus mission. It's called Venus Orbiter Mission, or Sukriyan 1. And also there will be a series of missions called Chandrayaan 4, 5, 6, so on and so forth, leading finally to putting a man on Moon, as is the already the roadmap given by our Honorable Prime Minister. Then, of course, we are also working towards the study of the potential sites for extraterrestrial life. So, be it on Mars or some other extraterrestrial bodies, we are very much interested, because the fundamental motivation behind this is that we would like to search for whether we are all alone on this Earth, or also there are existence of extinct or extant life on other planetary bodies, and maybe in some of the exoplanets or in the whole of universe. Of course, another interesting topic that we are basically trying to understand is or quantify is the in situ resource utilization. This is very much important, because we are talking of this moon habitation on Moon, so that we can further go for deep space explorations. And in order to do that, you need water and other resources to be there, so that you can build some kind of huts for the astronauts for further explorations. And also you can use the water for as a fuel purpose. Then we have this dedicated planetary atmospheric study team, and they are looking into the atmospheric chemistry and dynamics. And these are the major goals under which we are working. And of course, as I told, that the major emphasis is to use or in a maximum capacity the data sets that are being obtained from the ISRO's mission. Vis-a-vis, we also look into the other missions data sets to come up with a holistic picture of the scientific problem that we would like to address. And then, of course, analog is an extremely important thing. If you want to understand the processes or mechanisms that is operated on some other planets or is being operational, then you have to consider Earth as the standard reference. And another important thing is that here on Earth, you can go to the field and collect the samples and analyze them in a sophisticated analytical tools at various sophisticated labs, which is otherwise not possible for exploring other planets with robotic rovers, or even through manned missions, which are extremely cost intensive. So next, I would like to show you the beautiful liftoff picture of the Chandrayaan 3 and some of the images. And as we all know, that it was a historic day and achievement, I would say, on 23rd of August 2023, that India could successfully land robotic lander and rover on the Moon. And in that particular lander and rover, there are few experiments which were carried out, and many of the results are started coming from those experiments. To name a few, that we had alpha particle X-ray spectrometer from the Physical Research Laboratory, Ahmedabad, and it has mapped the elemental abundances in and around the landing sites where the rover could move. And the results were published in the very prestigious Nature journal. You may be also aware of that those results. And then we have this laser-induced breakdown spectrometer in the Progyan rover. And there was a shape experiment on board that propulsion module, I would say. Then we have this Chaste and ILSA. These are for seismic activities and to understand the thermophysical properties of the landing sites. These instruments were equipped in the lander itself, and they are also bringing out interesting results. So this is where the Chandrayaan-3 landed, and this is called Shiv Shakti Sthal, the Chandrayaan-3 landing sites. So and this is the OHRC image of before and after the landing. And after the landing, this Vikram lander's shadow can be picked up very nicely by the very high resolution OHRC imager at 0.3 meter resolution. So these are the images of the lander imager. You can see, and this is the ramp basically, and the Pragyan rover is just about to come out of the lander, and this is the deployment of the lander ramp. And these are the very high resolution lander imager cameras through which these pictures are obtained. This is many of you have already seen this, and this is the beautiful picture of the Vikram lander with the deployment of the Chaste and ISRO instruments. And this is captured by the Pragyan rover navigation camera. Okay, so just to give you a little bit about the moon, so which is our only natural satellite. So apart from having some kind of romanticism since our childhood days about the moons, there are so many poetries on moon, but there are something interesting to look into this body, which appears very gray in nature. But even though it is appearing gray, but it is quite interesting to look at. So the most established or most preferred hypothesis behind the moon formation is now called as the giant impact hypothesis, where object called Thea, which is almost of the size of Mars, collided with the proto-Earth way back around 4.5 billion years. And because of that huge collision, part of Earth's mantle that way went out, and under the gravitational force of Earth, the condensation of the material started happening. During that process, actually, there were accretionary heating, giving rise to the global magma ocean. And with time, this magma ocean got cooled, and various stratification has happened, giving rise to the lunar mantle and the crust. So if you see the lunar mantle composition, it is primarily made up of mafic silicates or dark colored silicate rocks. They are mostly the cumulates we used to call, and it is made up of pyroxene and olivine. So you need not have to remember about the names of these minerals and the rocks. And the rest of the lighter elements started floating on the denser mantle or the atmosphere. And then through slow solidification of that lighter elements, what we see, the brighter part of the moon is made up of, we used to call it as anorthosite, which is a monomineralic rock basically. So, and that is lighter and brighter in color. But you also see that we all know that the moon is basically tidally locked with respect to Earth, and therefore we only see the near side of the moon. And it has got lots of dark patches, which is also visible through bare eye. And these dark patches are nothing but the secondary crust of the moon, which were formed through the very hypervelocity impacts of various sizes, giving rise to large impact basins. And because of the deep puncturing through these hypervelocity impacts, decompression of the lunar mantle took place, giving rise to the generations of magmas. And those magmas are basaltic in composition, and basalt being darker in color, and it is almost that's why this appearance is coming. This dark appearance is there in the Mare basins. So essentially, if we talk about the lunar crust, we have two kinds of crusts. One is the primary crust or anorthositic crust, which is brighter in color, and then you have a darker crust, which is also denser, a little bit denser, and that is basically basaltic crust called Mare basalt.
আমাকে annotation করতে allow করছে দেখছি সেটা
So these are the beautiful pictures of the near and far sides of the moon. So as you can see, there are less number of dark patches on the far side of the moon, whereas the number of dark patches in the near side is much more. And of course, this is also a fundamental question that why there is such a dichotomy in the distribution of the Mare basins. So there are various hypotheses are there, but it is not well understood even now. So just to enthuse the audiences, particularly young minds, these are the various kinds of there are various kinds of features on the moon, and primarily there are billions and billions of craters, and they are of various natures. So here we are presenting an example of a complex crater. Complex crater is such where you will find a crater floor, and within the crater floor you will be seeing a central upheaval or central mound kind of structure. And this is called complex crater, and this is how complex crater forms. So it is basically because of the elastic rebound of the lunar crust, this kind of upheaval at the central portion of the craters form through large hypervelocity impacts. And there are billions of craters on the moon of various natures, from simple to complex to peak ring basins, and then large impact basins. So multi-ring basins, so on and so forth. So this particular crater is called Tycho crater, and this is a very young and having a very fresh ray systems. And in the southern hemisphere, in a full moon day, one can very easily see this crater with a telescope. And this is the close-up of that particular central peak. As you can see, this is the three-dimensional picture obtained from the terrain mapping camera from Chandrayaan-1 datasets. And this is the beautiful three-dimensional perspective view of the same crater central peak complex. So if you go further higher resolutions, you will find that at the summit of this particular crater, you find a large chunk of a large boulder, and there are so many small boulders. And you can also see some peripheral or cooling cracks. These cooling cracks are showcasing that these are the basically impact melts, and these impact melts got consolidated and gave rise to the cooling cracks. Similarly, in the right panel, you can see some kind of flow tongues. These are the flowing impact melts. It is wrongly written as lava, but these are the flowing impact melts, and they later on got consolidated. So these kind of beautiful images you can see with very high resolutions, and they will tell a lot of stories about how these regions on the moon are evolving, have evolved with time, with the geological time. So this is another interesting feature which is called lunar rill, and they are nothing but a collapsed lava tube. So you in the right upper right panel you will see that the flowing lava, and this is from the Hawaiian Volcanic Observatory. And once the lava flows and got exhausted, then you will find that the vacant tunnel. So what happens is that with time, this tunnel got collapsed once the lava moved out of this channel. Then what remains is the collapsed lava tubes. But here in this TMC image, what we would like to stress upon is that a part of the lava tube is also remaining intact. And those intact portions would act as a very nice natural shielding for the future astronauts to stay there. And for further deep space explorations, or if somebody wants to do some kind of habitations on moon, these are the locales where we should look for, because otherwise the moon being an airless body is extremely hostile. So this is the close-up of these reels, and they appear almost like a cobra hood. So they are also called as cobra-headed reels. And these are sinuous in nature. So they are also called as sinuous reels. Okay, so apart from these high resolution morphological studies, we do spectroscopic studies to understand the chemistry of the lunar crust. And we use mostly the hyperspectral sensors from Chandrayaan-1 and Chandrayaan-2. So here is an example I would like to show from the Chandrayaan-1 moon mineralogy mapper data. And this moon mineralogy mapper instrument was built by JPL NASA. It was flown in Chandrayaan-1. And this particular instrument has brought a huge amount of discoveries from moon. And to name a few is, of course, the widespread hydration on the moon, particularly in the lunar polar regions. Then we have this the discovery of magnetic water on the moon, and then a special new kind of rock type, which is called OS suite of rocks, or orthopyroxene olivine spinel suite of rocks. And I mean, it has given us more number of questions than giving the answers, and they are really interesting questions, and the whole scientific community is still trying to find out these answers. So we were interested in looking into some anomalous zones on moon, and one such anomalous zone is called Wolf Crater Complex. In case of Earth, you must have seen that there are two rock types which are extremely common. One is called granite, whereas in case of Moon or other planetary bodies than Earth, granite is extremely rare. So granite is nothing but a very high silica-rich rock, and this kind of rocks, while quite common on Earth, is very difficult to get on other planetary bodies. So this Wolf Crater Complex is one such rare place on Moon where you will see the granitic kind of compositions. So we tried to characterize these through various kind of spectrometers data sets, and we used diviner data, which is a thermal radiometer from again NASA's LRO mission, and that has got 3 channels in the thermal region from around 8 to 10 micrometer or 7 to 10 micrometers. And using these 3 channels, we can map the locations of the Restylane bands, or Restylane bands are the Christiansen feature. And this Christiansen feature is having directly linkage with the silicate composition. So if you go from the basic silicates to acidic silicates, there will be a systematic shifts of the Christiansen feature towards the shorter wavelengths, or there will be a blue shift towards the 7 micrometer region kind of location. So based on that, we'll be able to understand whether this is a basaltic kind of composition or granitic kind of composition. So we tried to do that. And these are the high resolution images of this Wolf Crater Complex, and many features were mapped in these images. So you can see there are minor grabens, and then mode structures, then domal features, all those things were mapped. And then there is the NASA mission called GRAIL, using GRAIL, which is basically gravity recovery and interior laboratory experiments from NASA. And using this GRAIL data, we could analyze the underneath structures of this Wolf Crater Complex. And we found that there is a gravity low because of the less dense materials right along the central part of the Wolf Crater Complex. And that should be corroborated very nicely with granitic kind of compositions. So that very nicely that has come out from these studies. And also we tried to analyze the mineralogical part of it. And based on that, we could come up with a geological model explaining how this Wolf Crater Complex has formed and evolved with geological time. So what we did is that we used multiple datasets from multiple missions. And then we found that the composition is silicic in nature. And while there are other silicic complexes on Moon where you get lots of magnetic water, this particular region is also interesting because it doesn't have much of water in it. And without having water melting this basaltic, mafic mantle is very difficult in order to generate calcic kind of compositions. So we tried to propose what could be the possible explanations behind the formation of this kind of acidic compositions on the Moon. So if you have a suitable protolith and if you have a basaltic underplating, that could be a possible reason behind formations of acidic rocks. So I'll not get into the much details of this. So there is another interesting study which where we used we wanted to study the part of Gardner crater using the IARS datasets. And this Gardner, if you see at very high resolutions, you will see very beautiful impact melts and the flowing patterns of the impact melts on these flanks of the inner flanks of the crater. But we wanted to do some kind of AI/ML based or automatized techniques to extract the spectral end members or the mineralogical end members from the data. So using various techniques, we could successfully come up with 3-4 end members, and that was presented in this particular work. And Dr. Tausif Ahmed is the lead author of this particular work. So Gardner region is again another interesting mega dome region or mega volcanic region on the moon, and it has got both mostly high calcium pyroxenes or basaltic kind of compositions, but the adjacent regions are noritic in compositions or low calcium pyroxenes rich compositions, and very nicely picked up by IRS data. Okay, so we were just talking about, we were showing the pictures of the landing sites, Chandrayaan-3 landing sites, and these are the data sets of Chandrayaan-2 imaging infrared spectrometer of the landing site. And we tried to quantify the surface temperatures of this particular landing site region. And after removing the thermal emissive component from the reflectance data, we also tried to quantify the presence of water and the concentrations of water in this particular region, which is called Shivshakti and the adjoining regions. Okay, so there are another kind of craters called floor fractured craters. It is having lots of fractures inside the craters, and sometimes these fractures you will also you may get some kind of lava flows, or sometimes you have pyroclastic deposits. In this particular case, this is a Atlas crater. You have this two dark patches in the southern and northern part of the crater, and they are mostly pyroclast, and they are high titanium rich materials, mostly ilmenite. And then you have seen this colorful picture where there are different colors highlighting different kind of mineral composition. So it's a very interesting region where you have lots of mineral diversity, starting from spinel bearing rocks to olivine bearing granitic rocks of mantle origin or orthopyroxenites, and even the crystalline plagioclase bearing anorthositic rocks. So this is how, if you have a very well calibrated spectrometer, VNIR spectrometer, or maybe mid-IR or thermal spectrometers, you can easily discern the compositions of any planetary bodies. So again, here also in case of Atlas, we could successfully quantify the presence of water. Not only the presence of water, but the water of two different genesis. So one particular water which is associated in the lunar crater floor is mostly formed through solar wind proton induced hydroxylation, and therefore it is called exogenous process. Whereas there are waters associated with the nominally anhydrous minerals like olivine and pyroxenes, and these are the waters which are residing inside the crystal lattice of these minerals, and they are brought from the interior of the moon. So these kind of studies are extremely important if somebody is interested in doing the lunar water budget. Okay, so these are the locales, and these are the spectrometer data are extremely fantastic in putting the constants on the lunar mantle water content. And that also is having direct connotations with the moon forming impact event itself. So these are the stages of evolutions that we tried to come up with to explain that how this particular Atlas crater might have evolved in a geological sense, time scale. So a few of our studies, there is a lunar science nuggets prepared by Lunar Exploration and Analysis Group. This is a global lunar community hosted at USRA LPI, Lunar and Planetary Institute, Houston. And we are happy to let you know that 3 of our papers are cited in that particular lunar science nuggets as interesting and important contributions since 2000, or the major discoveries since 2000. And these are this discovery of endogenic water or magnetic water at Compton Milkovich volcanic complex on the far side of the moon. Then we have another interesting crater called Theophilus, and we could report the presence of magnetic water again in the central peak of this Theophilus crater. And then we could also establish for the first time this Compton Milkovich volcanic complex as a ash flow caldera. So, and then we also saw that this Wolf crater complex can also be considered as a caldera, silicic caldera, and they are very rare on the moon. So, and then whatever mineralogies we talked about the discoveries of spinel on the moon, and they are extremely important because these findings help us in planning various kind of petrological experiments or experiments leading to the understanding of how this kind of mineralogies or lithologies can form. So these are just some examples of how the experimental petrology works. In particular, this particular case, I would like to showcase that people have started with two different compositions, and this is a famous work by Stephen Elardo and his team in New Mexico. And they started with two different compositions. One is Taylor's whole moon, and the other one is Long's primitive lunar upper mantle. And if you start with these two different compositions, where in first case, Taylor's whole moon, it is considered that the amount of refractory elements on moon is twice that of that on the Earth. Whereas in case of the other composition, that LPUM, we consider that it is almost similar compositions as that of the starting material as that of the Earth. But when we consider initial composition which is engaged in this refractory elements, then you find a field where you see this olivine, spinel, and OPX kind of a region or phase in these phase diagrams. So there is a broad region corresponding to this olivine, orthopyroxene, and spinel field, which is completely missing in the other compositions. So this kind of studies are actually helping us to pinpoint also that what could be the starting point for this kind of lunar compositions, because now through spectroscopic observations from Chandrayaan-1, it is sure that we have this olivine, orthopyroxene, spinel kind of compositions on the moon. So I think that's it. I'll stop over here, and this is a team that we are talking about, and Sri Aditya Dagar, he is a geophysicist, and he did his geophysics from IIT Roorkee. We have Dr. R. Fani Rajsekhar. He did his PhD from Osmania University, and he earlier worked at NGRI Hyderabad, National Geophysical Research Institute. Then we have Dr. Sriram Sharan Veeravarasu. He did his PhD from SAC and then went for a postdoc at Arecibo Observatory, and later on he moved to Lunar and Planetary Institute, Houston, and then from there he came back to SAC again. Then we have Sri Rohit Nagori. He is from the physical sciences background from Indian Institute of Space Science and Technology, Tiruvananthapuram. Then Dr. Sumit Pathak is there. He did his PhD under my mentorship, and also Dr. Shubham Sarkar. And Sumit is presently assistant professor at Parul University, whereas Shubham is working as a postdoc fellow at ISRO Birampur. Then we also have Dr. Mamta Chauhan, presently a scientist at IRS Dehradun, and Dr. Satyaprakash Oja. He is looking into the radiative transfer simulations for the Venusian atmospheres for retrieval of surface emissivity. So I'd be happy if there are any questions. So I would stop here. Thanks.
Thank you so much, Dr. Bhattacharya, for the fascinating and insightful exploratory exploration of planetary sciences. Due to time constraint, we are not taking the questions right now. We will ask the participants to write down the questions in the chat box, and we can forward it to you, or we can discuss it at the end of the session today. So will that be fine?
Yes, absolutely.
Okay. So, thank you, sir. And we have with us Dr. Radhatomar Goswami now. So he is our respected Pro Vice Chancellor and Dean of School of Engineering and Technology. So I would request sir to address the audience or participants.
Thank
Sir,
you.
if you are
Yes. Thank you,
yes.
Shatarupa. This is really I was just listening to Dr. Bhattacharya's speech, definitely in the midway, but it was very much enriching, definitely. So on behalf of, first of all, on behalf of the Adamas University, and to be very specific, from the Department of Physics, along with all the faculty member and the HOD and Dean, uh, I welcome all the speakers from day one and day two. Then day one specifically, Dr. Satadru Bhattacharya, who has just finished his talk, then followed by Dr. Naveen, Vetcha, and Dr. Kaushik, Mitra. Tomorrow also do have another set of people, another people speaker. So I welcome all of them on behalf of the physics department, and Dr. Momita De, who is the dean and the HOD of the physics. And this is really a great part of that physics department is organizing this physics pulse. So any students, researcher, this would be this is really a fascinating part, because they get to know many things about that which is not being, they may not know many things unfolded, and it's there about the NASA and ISRO. People have a dream. The students have a dream of joining this organization, working with this organization, and even doing the internship. And the why you should join, it was clearly mentioned about that you can hear directly from NASA and ISRO and other people, those who are associated with them. Then you can think of that career space. Your space in career can be in with the space and the physics, because nowadays people have a, because if you do not know the science, then all of your engineering, anything is incomplete in true sense. So my best wishes to all the participants. Listen to them. Definitely time, because of the time constraint, may not you can ask directly or hear from their answer from the concerned people, concerned person. So definitely you, in the chat box you mention, as Shatrupa mentioned, your query, and later definitely will be convey this thing to the speaker and they will answer your query. My once again thanks to all of them and to the speaker as well. Thank you.
Thank you, sir. We truly appreciate your motivating words. So, to introduce our next speaker, I would now like to invite my colleague, Dr. Papya Dhara from the Department of Physics. So, over to you, Dr. Dhara.
Thank you, Shatarupa. Am I audible?
Yes, you're audible.
I hope so. Okay. So it is my absolute honor to introduce our next speaker, our distinguished speaker, Dr. Kaushik Mitra. Dr. Kaushik Mitra is an assistant professor in the Department of Earth and Planetary Sciences at the University of Texas at San Antonio. He is a low temperature experimentalist and aqueous geochemist whose research explores the formation, evolution, and alteration of geological materials under planetary surface and subsurface conditions. Dr. Mitra completed his integrated BSc and MSc in applied geology from IIT Kharagpur and later earned his PhD from Washington University in St. Louis. He has also worked with the Indian Space Research Organization, that is ISRO, and held a postdoctoral position at Stony Brook University. One of his most notable research contributions was published in Nature Geoscience, where he challenged the widely held view that manganese oxide on Mars are evidence of oxygens in the planet's early atmosphere. His study proposed insists that this oxide indicate an active and complex halogen cycle, both in the past and present Martian surface environment. So this groundbreaking work received attention from the multiple international media outlets. It's really exciting to have you here, Dr. Mitro. And now I invite Dr. Mitro to enlighten us with your talk.
Thank you so much, Papia, for that wonderful introduction. I would not have written that introduction for myself, though. But anyway, thank you so much, the entire team of Adamas University, to invite me. And I think Shataduda actually probably played a role in suggesting my name. So thank you to Shataduda as well. So here at the onset of the talk, I would like to mention two things. First, the students are going to feel, students and anyone listening to me are probably going to feel cheated by two things. First, I do not look the same as the image on your ad or the title slide suggested. I had beard and hair back then. So now I've like recently shifted. So I do not look the same, but I am the same person. The second thing is I am not a physicist. I am a geochemist, and I work in planetary sciences at the intersection where we have different kinds of science background people coming in. So we have physicists coming in, we have planetary sciences, we have geological sciences, we have biologists, we have data scientists. All of us, like, we work together towards understanding planetary science problems, trying to solve them. And we are also trying to understand how life might have originated in the solar system, or if there is life elsewhere in the solar system or not. So we call this area of research astrobiology. So given this is like a physics department talk, I've never been invited into a physics department lecture before, but in today's talk, I will not talk about physics specifically, but what I'll try to talk about is how we study planetary sciences and a field of astrobiology that takes in different branches of sciences, different scientists, different engineers to actually solve a problem that is such broad in scope. What I mean by this is, one person from one discipline cannot possibly solve such big questions. Okay, so if you have questions such as if there is life on in the solar system or not, we would need the physicist, we would need geologists, biologists, data scientists. All people come together and then think about these problems. So when all the great students in here from class 11, 12, maybe undergraduate universities, they're listening to us, what I want them to actually understand is, you cannot just think about your own discipline to start off with. You have to think in a way that transcends the boundaries of the science. So do not limit yourself as tagging yourself by being a physicist only. So in order to be in planetary sciences, in order to join ISRO or NASA or do planetary science research, you have to think not only as a physicist, but maybe also as a chemist, also as a geologist, maybe a biologist. All these kinds of things, you have to at least think about these questions, talk to different people. Okay, so with that, let me start my presentation. I think I can share the screen. Is the screen visible?
Yes, sir. Yes, sir. It is visible.
Okay. So I'm just going to hide this. Okay. All right. With that, let's start. So today we'll be talking about astrobiology and not physics in specifically, okay? But we'll be thinking a lot about all these different kinds of different branches of sciences when they come together, and how do we think about astrobiology? Now, we have so many different, so in our universe, there are multiple galaxies. In each of these different galaxies, you have several, like, millions and billions of stars. Each of those stars will have many, many different kinds of planets. It is very odd to actually believe that no other planet in this entire universe will not have life and only Earth will have life. It is very difficult to assume because the numbers are so staggeringly high. It's about 10 to the power 23 or 24 planets are supposed to be present in our entire universe. There is no way that we are the only people in the universe. There will be other life forms, whether they look like us or whether they are carbon-based life forms or they are water-based life forms or not. That's an open question. We do not know that. Also, whether we'll be able to establish contact with them is another open question. We do not know that. But many philosophers, many scientists, including me, I do not believe that we are the only people in the universe. There has to be life forms in the universe just because the numbers are so high. So statistically speaking, there will be life forms elsewhere in our universe other than Earth. The two open questions in astrobiology are these. Do we have life forms elsewhere in the universe? And how did life actually originate on Earth? Now, having said that, when we talk about planetary sciences, why do we care about life outside the Earth? Because clearly we are living on Earth. We do not possibly know that there is life in our solar system, maybe in Moon, Mars, or the other terrestrial planets. We do not know that. So why do we care about planetary science research? Is one of the major questions that I had. Like, what is to be gained when you're looking at the Moon? Or what is to be gained when you're looking at Mercury or Mars, for example? To actually understand that, let's look into this simple graph, okay? So in here, as you can see, this is what we call a geological time scale of the Earth. What this means is, on the right-hand side, you see all these numbers. These are the numbers that represent billion years before present. So what 2.5 actually means is this was 2.5 billion years before this time, okay, where we are currently. This is 4.5 billion years before time. And if you can imagine this timeline being extended towards the right, you will find the time point 0 where we currently are situated. Okay, so this is 4.5 billion years before present. And this is the time where most of our solar system, our current solar system, actually was formed. Sun formed about 4.5 billion years ago. There are other planetary bodies like Earth, Mars, Mercury, they all formed roughly about 4.5 billion years ago. So it's very important to understand what time they actually formed. Now, so Earth formed at 4.5 billion years ago. We have 4.5 billion years of history between now and then. Life must have formed somewhere in the middle. And the current research that we have, that happens in geological sciences mostly, some geological sciences, and we have a field called geobiology and paleontology, which is the study of fossils. They have all come up together with these numbers in which we think that life originated somewhere between 3.9 and 3.6 billion years ago. So in here, between 4.0 and 3.8, we have the oldest rocks on Earth. Some of the oldest microfossils are between 3.5 and 3.2 billion years ago. These are the stromatolites. This is an image of a stromatolite from Western Australia. And then we have really old minerals called zircons. So this is zirconium oxide, ZrO2. These are very robust minerals that have been formed very early in the solar system or very early in Earth history, but we still have a bit of them left. The thing about Earth is, because of plate tectonics, most of these really old rocks are now gone. So many of you might have heard that on Earth, we have all these different plates that make up the upper crust or the lithosphere of Earth, and these plates are constantly moving. These plates, the movement of these plates can be three types: convergent, in which they come together, come towards each other; divergent, in which they move away from each other; or transform, in which they are just running past each other in a fashion such as this. Okay, now, the thing is, all the earthquakes and all the sources of the seismicity that we see on Earth are a result of these plate movements. Okay, because of these plate movements, old crust is being removed or destroyed, and new crust is forming every day, even now. Okay, so all these old crust that was, we call them primary crust, all that primary crust is now gone. Only a little bit of that remains with us for us to study. Now, if we want to study the emergence of life, we would need these really old rocks, but we don't have those really old rocks. What do? Here comes the importance of studying different planetary bodies. In this context, there are different reasons of studying planetary bodies, but this, for me, is one of the primary reasons of studying different planetary bodies like Mars, which I study. Okay, so if you need to study what was happening in our neighborhood about 4 billion years ago, when life was actually forming on planet Earth, we need to go to planets like Mars and see what was happening there, because about 50% of the crust that the planet Mars has is about 4 billion years old. So we have really old rocks that are pristinely, they're preserved on the surface. So if you want to study what was happening around that time when life was originating in our planet, we have to go to a different planet and study it because of the dearth of the information that we have on Earth. So this is one of the reasons to study to study emergence of life on Earth, or astrobiology. Okay. Now, one of the main questions here is, how did life begin? It seems like a very, very simple question. Okay, I will not name this scientist, and I'll leave it up to you guys to actually figure who this scientist was, who was actually trying to understand the origin of life at the first. So this scientist was the first person to have actually undertaken this journey of like understanding the origin of life. Because I want the students in here to actually appreciate this question, that at one point of time, there was no life. There was just inorganic elements. These are just some elements that are present on the surface of Earth. But then something happened that took all those non-living elements, and then life began, life originated. How did that thing begin? We have no idea. This is a very simple question, but a very difficult one. Like simple in a way that it is a very primary question, but we do not understand how life actually formed. Now, people thought that there was a spontaneous generation mechanism. What I mean by spontaneous generation is, like, if you have like bread lying on the surface or lying on your table, and you leave it for like 30 days, what will happen? Fungus will try to erupt. If you have meat lying around for a long amount of time, you can see that small maggots kind of like arise from the dead animals' carcasses or meats, things like that. So what people thought is life always originated from a previous life. Okay, but the problem here is the answer is true here. But the problem here is, how did the first life form begin? It is questions such as these that many of us, the geologists, the geochemists, planetary scientists, data scientists, biologists, physicists, we are all coming together. We're trying to solve this very basic question: how did the first life form? I will not get into the details of this, but I want you guys to actually think about these questions. And for the people who are interested, you can just Google Simon's collaboration on the origin of life, and you will get a set of questions that we are trying to solve. Okay, now life as we know it is one of the things that we can start our investigation of how life must have formed. Okay, so this is a tardigrade. Okay, I'm not getting into like the details of this, but many of you must have seen this organism. This is not science fiction. This is not hypothetical. This organism actually exists on, like, in our universe, in on Earth, in some of these spaces that we inhabit with. Okay, we call these things extremophiles, and we'll get into what extremophiles are in a moment. But let's first define life. The simple definition of life, as NASA defines it, is a self-sustaining chemical system capable of evolution, or Darwinian evolution. Okay, now with that, if we want to know how life must have originated, we need to first understand what are the different kinds of organisms that currently are there in our world. So there are primarily three types of organisms: bacteria, archaea, and eukaryotes. I'm not getting into the biology of the things, but if you have to understand, what I want you guys to understand is this: life is becoming more complicated as time is passing by. Okay, now when you go back in time, things would have been more simple. Like if you go back in time, if you just go 10 million years ago, or 50 million years ago, or 100 million years ago, things would have been much more simpler than what we have today. So when you go back in time, things become simpler and simpler, and all these different types of organisms must have a common ancestor. Okay, like we call this common ancestor for all these three types as a last universal common ancestor, or LUCA. The idea is, if we can actually find the last common ancestor for all these organisms that currently exist, we get to understand the origin of life a little better, right? Now, when Earth was actually forming like 4 billion years ago, 4.5 billion years ago, the environment of Earth was very different than what we have today. Currently, the environment is very, very clement. It is global warming and environmental uh, like problems are currently happening. There is a global climate change, but in general, in a 10,000 or a 1 million time scale, things are very, very stable. Things were very hot and very extreme when the last universal common ancestor was actually probably forming, or during the origin of life. It must have been very hot, gaseous environment, and it could have been like very acidic or very basic. So not that good environment for life. But the Leuca probably existed in one of these extreme environments. Okay, and we call these extreme environments, the organisms that are present in those extreme environments, as extremophile organisms. Like, so there are thermophiles that exist in temperatures in 50 to 80 degrees Celsius, hyperthermophiles, and all these different kinds of organisms. For example, on Mars, do we think that if there is life on Mars, we will have organisms similar to Earth? I don't think so, because the surface of Mars is so cold and so replete with different kinds of radiation environment. The type of organisms that probably would exist on Mars would be a type of extremophile. So in order to understand what Leuca was, how life originated on Earth, and what might be an organism living on a different planet, we need to study the extremophiles, right? So like, this is one area of like active research in planetary science and astrobiology. Okay, so now if we try to understand where Leuca existed, because these were extreme environments, we now need to understand the chemistry for life. Because what temperatures do they need? What was the chemical composition of the fluid in which things were originating? Was it very acidic? Or what are the different elements required for the origin of life? Questions such as these. Now, to understand this, let's understand the basic ingredients of life. Like, what is the absolute basic ingredients of life? Okay. Now, since you guys are in like class 11 or 12, or maybe you will going into first year or second year of college, you will be having a lot of parties, right? So let's try to understand what are the major constituent or the basic components of a party, and then we'll try to understand what are the basic constituents of life. Now, the basic constituents of a party are, the first important thing is the guest. Without the guest, you don't have a party. The second important component are the hosts. The hosts make it possible for the guests to have meaningful conversations, to make friends, and so on. And then you need to have food for the party to sustain. So there is no party without a food. Life, if you think about, follows a similar pattern. So there are these basic ingredients of life, right? So their elements are the things with which life is actually made up of, the building blocks of life. Okay, so you have all the different elements. We call it the sponge elements, or CHNOPS. So like, you have carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These are some of the very minimum elements that are required for the origin and for the sustenance of life. And there are many other elements that we also need, but we are not going to talk about that. The medium is the water. So water acts as the host. It allows all these different elements to come together, interact, and form meaningful bonds. And then you need energy, you need food for the origin of life and for the sustenance of life. Okay. Now, since we need those elements, these elements need to come together to form biomolecules. And we'll get to the biomolecules part in a bit. But this is a plot in which I'm plotting the atomic number on the x-axis and the abundance on the y-axis. And this is a logarithmic scale. That means each unit is like 10 times more abundant. So you can see hydrogen is the most abundant element in the solar system. It's the simplest, is the most element, and you actually form hydrogen, helium as some of the major elements during Big Bang nucleosynthesis. So nucleosynthesis is what you will study in physics, we study in planetary sciences, is the process of making elements. So there are different kinds of nucleosynthesis. The two major ones are Big Bang nucleosynthesis, in which we are mentioned in here. So you have hydrogen and helium, basically these are being produced, and then you have stellar nucleosynthesis. What this means is the nucleosynthesis or the formation of elements that is happening in cores of stars, right? So like all the elements that we all are made up of have been made in a star somewhere. So like when people say that he's a stellar human being, it actually is true, because all the elements that you are currently made up of, everything, all the atoms that you are made up of, were actually produced in a star somewhere, sometime in the past. So that this is like a spectacular thing to just realize, like how special you are. Like everything that you're made up of, you have been made in a star somewhere. Okay. Now, I'm not getting into the nucleosynthesis business in here, but the thing is, all these elements needs to be prepared or needs to be produced somewhere. These elements, one of the most important elements in here is carbon, because carbon forms the base or like the framework in which we all are made up of. Like, so all living life forms that we know till now, all life forms are carbon based life form. We do not know any life form anywhere on earth that are not carbon based. There's another thing. You must, all the students in 11, 12, if you're taking chemistry, and I think you're taking chemistry, so I don't need to impress upon you like the properties of carbon and organic chemistry, right? So we are also made up of water, right? So we are also 70% water. So we are carbon based and we are water based. I want you guys to like remember that. Okay. Now, moving forward, all these carbon molecules or the carbon-based molecules are coming together and they're forming things called the biomolecules. And these are the different things that a human being or like most of the complex life forms are made of, right? So we have fat in our body, we have protein structures, your muscles are made up of the proteins, you have carbohydrates or the cell structure, and you have nucleic acid, the DNA, RNA, all these kinds of things, right? So all these are made up of the elements. Now, organic carbon is very common in the universe. So in the molecular clouds, in carbonaceous meteorites, so there are some kinds of meteorites, we call them carbonaceous meteorites, they have a lot of organic carbon. And there are other different places in our universe that have a lot of organic carbon. So I want you guys to remember that organic carbon is not rare. But what is rare is the presence of specific kinds of organic molecules in specific concentrations. Not getting into the details of this, but organic chemistry is what like deals with all these kinds of things in the universe. Okay. Now, the next very important thing is water, because all the action that is happening, origin of life and the sustenance of life, is impossible without water. There are other molecules or other fluid molecules like methane or ethane that are there in planets like Titan. So Titan is a moon of Saturn. It has lakes of ethane and lakes of methane, but it does not have water. The polar property of water makes it possible to dissolve different kinds of polar molecules. And you must have heard this term, like dissolves like, and why water acts as a universal solvent. Other molecules, other fluids like methane or ethane cannot act as a universal solvent for the elements that we are concerned about. Okay. So my 30 minutes are approximately going to be over in about 5 minutes. I'm not going to extend beyond that, but I'll like quickly go through the source of energies that we have in our solar system. So there are different kinds of energies. The food that we were talking about, there are different kinds of energies that are available to us. There is heat energy, nuclear sound, different kinds of chemical energy. But life cannot eat everything. For example, if you go to a party, some of your friends might be vegetarian. They cannot eat meat or they don't want to eat meat, right? So not every person eats everything. Life is like that. Although there are energies available, doesn't mean that life will be able to utilize that energy for their origin or for their sustenance. Life can only use two types of energy sources. One is a redox reaction and the other is light. So you must have heard about this term photosynthesis, and there is also chemosynthesis, but we are not going to get into this business today. I just want you to know that photosynthesis and chemosynthesis are the types of energies that life can actually use. So there is more that I wanted to cover, but with I'll respect the time for the other speakers. But what I'll do is I will direct you to my YouTube channel that has this course called. If you go to the playlist, if you just search Kaushik Mitra UTSA, you'll be able to find my YouTube channel. If you go to the playlist, go into planetary science, you will be able to see a short course on astrobiology in which I have recorded about 6 hours of lecture on this particular topic. There are other topics as well, but for today, I'm just redirecting our students here to planetary geoscience course in which I discuss all these things, all the astrobiology things in great detail. And I'll stop there. And I'll be happy to take any questions at the end of the talk. So thank you so much.
Thank you, sir. I must say that it was truly enriching talk, and I'm sure that it will spark lots of curiosity among us. And as a result, if you see, there is lots of questions in chat box, but as you know, there is a time constant. So we will convey all the questions to our sir, Kaushik Mitra sir. I hope sir will be happy to answer those questions for our audience. Thank you so much, sir. So it is really our privilege that you are here, and it was really nice talk. Thank you so much, sir.
Thank you so
So
much.
now, thank you so much, sir. So now we will go for our third speaker for today's evening session, and I would like to invite our senior professor, Professor Aparajita Bhattacharya, madam, to introduce our third speaker. Ma'am, you are not audible. No, I think there's some problem.
Is there any problem?
Yes, yes, now you are audible. Just increase. Yes, yes.
Yeah. Thank you, Papia. And it is my absolute pleasure to introduce Dr. Naveen Vetcha to this audience. Dr. Vetcha is team lead for Aeroscience team at Eminent Space Exploration Division, supporting the engineering services and science capability augmentation contract at NASA Marshall Space Flight Center in Hartsville, Alabama. His prior role on the contract include team lead for technology development, team challenge manager of NASA Centennial Challenges program, and liquid propulsion analyst for RS-25 engines that powered the core stage of NASA's Space Launch System rocket. Prior to this, he worked as lead analyst at NextSolve for NASA James Webb Space Telescope Sunshields. He was also adjunct faculty at the University of Alabama, Huntsville College of Engineering. He's an associate fellow of American Institute of Aeronautics and Astronautics. Dr. Vetcha received his MS and PhD degree in mechanical engineering from University of California, Los Angeles, MTech in Mechanical Engineering from IIT Kanpur, and BE in Mechanical Engineering from Osmania University, India. So we are really delighted and privileged to have Dr. Vetcha as a speaker in this Physics First program. So I just invite Professor Vetcha to deliver his talk.
Hey, thanks for the kind introduction. Hello, everyone. Well, thanks for staying up this late to listen to us, and it's a privilege to be delivering this talk to you all. So let me share my screen. I hope you can all see my screen properly.
Visible.
Yes, yes, it is visible,
Okay,
sir.
great. Let's see. I can't see it on my screen, so I'm assuming it's all good on your side. Because I'm working with multiple computers and I'm at NASA, so we can't use Zoom.
So it is like career journey now. It's showing.
Okay.
Yeah.
Can you see I'm moving the charts?
Oh, so it's still in career journey, but the first page, I guess it's in green, right?
Don't see anything green. Let me do this. I can always come out of the presentation mode and just show my screen. What about now?
So we can
you
see word file career journey. Amentum. How physics
And
shaped
then
my then career journey.
I just moved to the next slide.
No, it's still stuck in the career journey slide. So went back to the Amentum page. How physics shaped my career.
To share.
Yeah,
Can you change?
now it's changing. Physics concepts that propelled my career. Yeah. So
Okay, great. Thank you. So I'm at NASA, and we don't use Zoom. We can only use browser mode, so probably that's the problem. Thanks again. Dr. Mitra actually laid down it clearly in the beginning, as he said, as you venture into the physics world, you can't just think about just doing physics sitting in your cubicle or in your room. You have to work with people, other people, engineers, chemists, and all that, if you want to apply your physics knowledge to understand the universe. So I have all my engineering background, but I wouldn't have reached this stage without knowing the physics concepts. So here is a quick snapshot of my career journey after I graduated from University of California, Los Angeles. I mainly worked in something called nuclear fusion, which is kind of creating an artificial star on Earth. If you want to learn more about this, Institute of Plasma Research in Gujarat is very much involved in this kind of project. It's an international project called ITER, International Thermonuclear Electro Reactor. So in all the nuclear reactors that you ever heard of use nuclear fission, but going forward, humanity wants to achieve this nuclear fusion in a confined space, just like the picture shown here. And just to give you an idea of the reactor size, here is a 6-foot tall person per scale. This how big the reactor is. And the plan is to have a hot plasma here in the D-shaped a toroidal vessel, and you heat the plasma to up to 150 million degrees centigrade. That's the temperature at the core of the plasma, and that will cause nuclear fusion reactions. And mainly to the fuel that will be used here is deuterium and tritium. And as I said, India is also part of this big project. And my PhD was to understand something called the fluid flow inside the blanket, just right outside the walls of this D-shaped vessel. And we use lead lithium to extract that heat that is coming out from these nuclear reactions. And the reason we use lead lithium is tritium has a half-life of 12.5 years. And that means there is no tritium in the atmosphere. So we need to be able to produce the tritium inside the reactor. So all the neutrons that are coming out at a particular energy from these nuclear reactions are coming through the wall and hitting or interacting with the lithium that is flowing inside these walls. And when lithium interacts with certain energy of neutrons, it will create tritium. But we need to be able to extract the tritium from this liquid. So my PhD was to understand how this liquid is flowing inside this wall with so many effects, like heating due to nuclear reactions and buoyancy effects because of the uneven heat distribution, and also there is plasma right next to it. So you need to be able to understand something like electromagnetism, fluid mechanics, heat transfer, thermodynamics, plasma physics, so all that. And then once I graduated, I moved into industry and focused on mainly developing physics models to simulate small reactors. These are multi-physics modeling. As I said, it's like a disk. You see a disk here that is nothing but a silicon wafer on which engineers want to dope using certain elements, certain semiconductor elements to generate chips that you use in your computers and all the electronic devices. And these manufacturing plants cost millions of dollars. But before you do that, you want to make sure the physics works and the reactor works. So you do computer simulations to understand that physics behind that, right? And after that, I got a chance to work on James Webb Space Telescope's Sunshield. I'm going to talk a little bit more about that, about the telescope and all that. And I was the lead analyst for all the 5 flight Sunshields. And once we delivered that final Sunshield, I joined this contract that I am currently on at NASA Marshall in 2016, mainly to analyze something called RS-25 engines, which are also a doped space shuttle main engines, if you know about space shuttles. And I'm going to talk a little bit more about that. And I supported about 30 of those tests, mainly developing models to understand the performance of those engines. And after that, I wanted to move to the science and technology side on the same contract. And I got a chance to work on technology development for extracting materials or mining on the moon so that astronauts can stay there for longer periods of time. Like, how do we extract any materials that we can use instead of launching them from Earth to the moon? Can we extract ice that is there in the permanently shadowed regions? That's actually the focus that we had on developing some robotic systems to be able to extract icy regoliths, like ice, dirt mixed with ice on the moon's permanently shadowed regions. After we ended that project in 2024, June, I got a chance to move to aerosciences, where I have a team of people, subject matter experts, looking into various aspects of launching rockets and understanding what happens if some debris that appears on the top of the rocket hits the bottom part anywhere. So mainly doing some kinematics and dynamics simulations, physics-based modeling, and what happens if a rocket blows up, either in space or on Earth or while ascending, all that. What is the impact on the infrastructure surrounding the launch tower and all that? So for that, we need to be able to simulate the physics of mixing fluids, like rocket fuel and oxidizer, and the blast dynamics, like how the pressure wave propagates into the surrounding atmosphere with what is the energy and all that involved in that. So a lot of cool stuff that we are doing. Let's go to the next slide. So before I go into two of the major NASA programs that I supported, I want to clearly tell you, I wouldn't have reached this position without my understanding of some basic physics concepts. Even though I'm an engineer, understanding this physics, a solid understanding of these physics concepts helped me jump from nuclear fusion to multi-physics simulations to Webb Space Telescope doing some kind of structural mechanics to fluid mechanics and now aerosciences. It doesn't matter which area of engineering you are in. If you understand the physics concept behind it, you will thrive. And here are some physics concepts that helped in my career. So with that, I'll jump into Webb Space Telescope. If you have never heard about it, NASA launched this back in 2021, and it's doing amazing science in the last 3 years. Actually, tomorrow, Saturday, July 12th, marks the 3rd-year anniversary of first images sent by Webb Space Telescope. Webb Space Telescope is located at something called Sun-Earth Lagrange point, one of the Sun-Earth Lagrange points. It's a L2 point. There are 5 of those. It is a kind of a stable orbit around Sun, and it needs a less fuel to keep the telescope. That's the reason why, one of the reasons why they chose the L2 point as a location for this Webb Space Telescope. There is also another reason, is this one, the electromagnetic spectrum. You probably all heard about it, or you will learn about it more. When I say light in day-to-day life, light is just the light from tube light or incandescent bulb that we are think are from sunlight. But for a physicist, astrophysicist, a light is the entire electromagnetic spectrum, all the way from gamma rays to radio waves. And by looking at the universe in each part of the spectrum, we can learn new things about universe. And the Hubble Space Telescope, which has been in space for like 36 years now, has been looking at the universe in the visible part of the spectrum. That means it is looking at the universe just like how our eyes are looking at our surroundings, but it can look at an object for a longer time than our eyes can. And our eyes are also small. And it has been amazing tool for astrophysicists to understand the universe. Now, it has a little bit of infrared capability, but Webb Space Telescope is primarily designed to look at the universe in the infrared part of the spectrum, and that too mainly near infrared and a little bit of far infrared. That's another difference between Hubble and Webb. And why do we need to look at the universe in the infrared part of the spectrum? Here is an example. On the left, you see something called meerkats and freshwater crocodile. By just looking at them in the visible part of the spectrum, you can tell some features of the meerkats. Hey, they have a fur, their region around their eyes is black and all that. Freshwater crocodile, you can see the pattern on its on its body or the skin. But once you put on your infrared glasses, you are actually getting some additional information. For example, meerkats are glowing, their stomachs are glowing, which tells us they have a higher metabolism. Whereas for freshwater crocodile, you can see the difference between the land and the color difference between the land and the crocodile, which tells me maybe crocodile was just swimming in the warm water a few minutes ago, and then it just came out and just resting. So that's why the difference in the temperature. So infrared is just a heat signature. and everything that you see, or you can't even see, like air and all the elements of the molecules in the air have certain heat signature, and infrared lets you see that. Another big difference between Hubble and Webb is the size of the mirror. Hubble's mirror is about 8 feet in diameter, and Webb's mirror is about 22 feet in diameter. Even though it's bigger in diameter, the crispiness of the amount of information that Webb is going to send us in infrared is about the same as Hubble that sends invisible. It's because just how the mirror size, the crispiness of the image is inversely proportional to the wavelength. And Hubble's wavelength is visible, which is shorter, versus Webb's wavelength, which is longer. So you need to have a bigger mirror to, and all those mirrors are gold coated with a very, very thin layer of gold so that it can effectively reflect the infrared light. And the entire telescope is kind of divided into two sides. Here is a small model. I think you can see it. So on this is the side where you have mirror. Maybe I can quickly turn off my background. That's okay. I can't figure that out. But here I have it model. So it's a big sun shield here, and on this side you have the mirror, and on this side you have all the stuff that can use to keep the telescope in properly oriented, like all the field and thrusters and all that. And then the back of the mirror, you have a panel in which you have all the science instruments. And on this, the mirror is always pointing away from the sun, and this sun shield is protecting the mirror from all the heat and light that is coming from the sun, because we don't want to blind the telescope with all the light and heat coming from the sun. It's because the telescope is looking at the universe in the infrared part of the spectrum. And that's the main purpose of the sun shield. On sun facing side of the sun shield, you can actually boil water. That's how hot it is. Whereas on the other side of the telescope, you can freeze nitrogen. It's about 40 Kelvin on the other side. And there is am I still there?
Yes, now you are
Yes.
there.
Yeah, sorry about the Zoom issues. But all right, let's move on. Here is my team. When we deliver the last layer, that can give you an idea of the size of this sun shield. There are 3 people standing at the center of this sun shield, and here is the crate in which we transport the sun shield from Huntsville, Alabama to Los Angeles, where this telescope was being integrated at the time. I talked about the instruments. There are 3 instruments that focus on near infrared part of the spectrum, and one that is focused on mid infrared part of the spectrum. And another reason why we look at the universe in the infrared part of the spectrum is infrared can go through or peek through the dust that is out there in the universe. A lot of stars that are being formed are forming in these huge clouds of gas and dust that stretched over several light years. And if due to that dust between us and the stars that are being formed, we can't see those stars. But once you put on the infrared part or infrared glasses, a powerful gases, of course, you can see through that gas and dust and see what is happening behind that. So here is an example. On the leftmost side, you have a cat's paw nebula, a nebula named cat's paw nebula, being looked at in the visible part of the spectrum by a Earth-based observatory. And you can see there are a lot of dark regions where it is a lot of dust. Whereas if you look at the same nebula in the infrared part of the spectrum, you can see all those light, small dots glow up. So those are all the new stars that are forming. If you want to know how much dust is present in a certain region, you have to look at it in the mid-infrared part of the spectrum, and that's what the rightmost image is showing. So it shows why we need to look at the universe in the infrared part of the spectrum. Other reason we want to look at the universe in the infrared part of the spectrum is with a visible light, we can only look into a certain point after something called Big Bang. We want to look at or observe the first galaxies, first stars that formed. But the universe has been expanding, and the light that left the initial, like very early on galaxies, has been stretched into the infrared part of the spectrum. This is a concept that you may have to, it will take some time to understand, but hopefully this talk will motivate you to go read about this. And, again, going back to the early galaxies, early stars, there is no way you can find them in the visible part of the spectrum because most of the light that left them has been stretched into the infrared part of the spectrum. That's why to see those early on stars and galaxies, you need to look at the universe in the infrared part of the spectrum. And for all of us, general public, a pretty image is nice, but for physicists, astrophysicists, they want to understand the chemical composition of a distant galaxy or a star or a exoplanet and all that. And the way they do that is to analyze the light. They distribute the light into its wavelength, and just like everyone in this virtual room has their own unique fingerprint, each molecule or ion has its own unique fingerprint, and that fingerprint comes out when it interacts with light. And we identified all those fingerprints by doing some experiments in the lab in the 19th and 20th century. So by looking at where there is a peak in the spectrum or where there is a trough in the spectrum, you can tell which element or which ion it corresponds to. So here is an example of a thin slice of an image that Webb took. Just by analyzing the light from the small red dot, you can actually see what are all the contents of that particular dot. That is a galaxy that is 13.1 billion light years away. So pretty amazing science that you can do with that. This is my last slide on Webb Space Telescope. Webb has a lot of goals to fulfill. One, to understand the early universe, how the early galaxies formed, early stars formed, and what happens when galaxies interact with each other. The concept that there's new stars form, new planetary systems form when galaxies interact with each other. And then star life cycle. Dr. Mitra talked about it. How do each star form? How planets form around those stars? We need to understand it better. And there are exoplanets. We want to understand the atmospheric contents of exoplanets. So that's another goal. Webb is also going to look at planets in our own solar system, not Mercury and Venus, because we are not going to point Webb never towards the sun. It's always pointed out from the sun. So multiple science goals, and just in 3 years, we had an amazing discoveries from Webb. So go to web.nasa.gov to learn more about it. All right, so second part of the talk, very few slides, is about Artemis program, which is NASA launched about 6 or 7 years ago with the goal of sustained human presence on the moon and learn things on the moon so that we can go to Mars for longer duration times. And here is a quick overview of what the plan is. We need to be able to first demonstrate launch vehicles that can safely take astronauts to the moon and bring them back. And we need to be able to have a certain space station kind of a thing that is orbiting the moon so that astronauts can use that as a long-term presence and then keep going down and up from the moon and back, just like how the astronauts are doing with the International Space Station. So they call it a gateway. It's much smaller in scale or size than International Space Station, but the goal is for it to orbit and the astronauts keep going back and forth from gateway to the lunar surface before we build habitats on the moon so that astronauts can actually land and stay on the moon for long duration while doing science and also exploring the moon's surface by using rovers. So as you can see, a lot of infrastructure need to be developed for astronauts to reach that goal. So this chart is just telling you we need to have rovers, we need to have energy technologies, whether it is nuclear or solar, communication technologies, and all that, and safely safe habitats, spacesuits, all that. So this slide again is telling you what kind of technologies we need to develop or have been developing at NASA in order to reach that goal of sustained human presence. We have a launch vehicle, we have a spacecraft that can send astronauts to the moon and bring them back. We need to have technologies for astronauts to go from the orbit and land on the moon. And NASA has been working with companies like SpaceX and Blue Origin in developing those technologies. And spacesuit, they need to have a proper spacesuit to be able to be out there for long duration, not just few hours. And Gateway, I mentioned, we need to also be able to develop all the infrastructure on the ground to launch the rocket and all that. So a lot of cool technology development happening. Here is the rocket that NASA has built with commercial partners to send astronauts to the moon. It's called the Space Launch System. And as I said, I got the opportunity to work on the core stage engines. Those are the engines all the way at the bottom of that rocket. And as you can see on the left side, just to give you an idea about the scale of this rocket, and I was there before launch of this rocket, and it was a fantastic experience just looking at this rocket at the launch tower. And this is only one configuration. NASA is furthering this configuration to be able to send a little bit more mass to the moon. And it primarily uses liquid oxygen and liquid hydrogen as the fuel for those four core stage engines that are at the bottom. So we already launched this rocket back in 2022, November 16th, a very surreal experience for me watching that rocket launch and come back. The spacecraft, Orion spacecraft came back and splashed in the ocean on December 11th. So a lot of, so that's a test demonstration mission, because before we put humans on that spacecraft, we want to make sure rocket performs as expected, and it did really well. And there are some lessons learned which we are already implementing on Artemis 2. The rocket is being stacked now at NASA Kennedy Space Center, and my team goes there often to make sure things are going well. And NASA is planning to launch this no later than April 2026 with these 4 astronauts, 3 American astronauts and 1 Canadian astronaut. And there will be a lot of demonstration of something called rendezvous techniques, how two spacecrafts can join in space, because we need to be able to do that in future missions. So they're going to attempt that in Artemis 2. So watch for this early next year. And this is my last picture. This is one of the tests I supported where we had to test the performance of the engine before we put it on the rocket. And we do these tests at NASA's Stennis Space Center in Mississippi, about 6 hours of drive from here. You can see the size of the test stand by looking at the vehicles, like the trucks that are out there. And I mean, it's a cool image. You can see on the top left, 4 of those engines installed on the back of the rocket. It's a cool image to show because there is a rainbow and all that. But in order to really appreciate this image, you need to know the physics. Why there is a rainbow and why the light inside the bow is very bright, whereas outside the bow, it is dark. Why is there a secondary bow? All this, I'm promising you, if you learn your physics, especially light, understand light and how it interacts with, for example, this is water, because as I said, liquid oxygen and liquid hydrogen are the oxidizer and fuel for this rocket. What happens when you mix oxygen with hydrogen? You get water. So the exhaust from this engine is water. And so that is all the water vapor that is coming out. And there is the sun that is at a particular angle, right? So cool image. And this is my last slide. I'm not going to talk about this, but I want to leave you with this, some lessons I want to share based on my career journey. With that, I'm open to any questions.
Thank you so much, sir. A big thank you to Dr. Vetcha for such a incredibly engaging and thought-provoking talk. So I don't think we will be able to take questions because questions are pouring all over through the chat box. But what I would request is to that way we can send you the questions, and if you have some time, you can reply them back because of the time constraint that we have. So, will that be okay with you?
Yes, yes, I'm on LinkedIn. If anyone wants to reach out and ask questions, feel free.
Sure, thank you. So, we are really grateful to have you and have the opportunity to hear from you, from someone who is working at a very frontiers of space exploration. So thank you so much.
Yes.
Now, before we close, I kindly request all participants to fill out the feedback form. The link will be shared in the Zoom chat box. So your feedback helps us grow definitely, and plus it will be required for issuing the certificates. So don't make spelling mistakes, students. So now, as we wrap up this stellar evening of the Physics Pulse 2025 Day 1, I would like to deliver the vote of thanks on behalf of our organizing team. First and foremost, our deepest gratitude goes to our distinguished speakers, Dr. Satadru Bhattacharya from ISRO, Dr. Kaushik Mitra from UTSA, and Dr. Naveen Vetcha from NASA for joining us from across the world and making time for this session, even at such unusual hours in your time zones. So, your talks have ignited curiosity and excitement in the minds of our students, I'm sure. And we are truly privileged to have learned from your experience and expertise, especially that you mentioned about physics and where it can take is really astonishing. So we sincerely thank the NASA Engages program for facilitating this event, especially Ms. Christine Peterson, speaker program lead and member of the astronaut appearances team, Office of Communications, NASA headquarters, for her generous support and guidance. A heartfelt thanks to our audience, the students, teachers, and curious minds from all the corners for your enthusiastic participation. We are grateful to the leadership team at Adamas University for their vision and continuous support in enabling such academic outreach. A special word of thanks to our Pro Vice Chancellor, Professor Dr. Radha Tamal Goswami, for his encouraging presence today, and also to Dr. Momita De, our Associate Dean and Head of the Department of Physics, for her leadership and guidance. I would also like to acknowledge the dedicated efforts of our program conveners and planning committee, whose tireless work behind the scenes made this event possible. A big thank you to the IT team and the technical support team for ensuring that everything is running smoothly online. And finally, I wish to express my appreciation to all my wonderful colleagues, the faculty members of Department of Physics, for your constant collaboration, teamwork, and spirit of shared purpose. So, thank you once again to everyone present here. Please don't forget to fill up the feedback form. We'll keep the session alive for some more time. And also, please don't forget to join us tomorrow on campus for day 2 of Physics Pulse. I'm sure we will meet many of you tomorrow with the workshops, exhibitions, and interactive activities designed to make science come alive. Thank you all and good night.
Shatrupa, please mention that there will be online session as well for tomorrow's talk.
Yes. So tomorrow the entire event will be the sessions, the distinguished lectures will be shared online. So you can also join online. Those of you who will not be able to come to campus. So that is also available for you.